Measurement System Analysis. Variable and Attribute MSA. Variable and Attribute MSA. The observed process variation can be due to 1. Variation from the measurement system and/or 2. Actual process variation. Variation from measurement system is due to 1. Variation from appraiser and/or 2. Variation from gauge. Variation from appraiser is the variation caused by the user not using the gauge as it should be used. Variation from gauge is the variation caused by the gauge due to inappropriate functionality. Variation from the gauge can be further bifurcated into accuracy, the difference between the average of observed values and the standard. Stability, variation in measurement when a person measures the same unit repeatedly with the same measuring gauge or tool. Reproducibility, variation in measurement when two or more persons measure the same unit using the same measuring gauge or tool. Repeatability, variation in measurement when the same person measures the same unit using the same measuring gauge or tool over an extended period of time. Linearity, the consistency of the measurement across the entire range of the measuring gauge. The actual process variation is caused due to variation from controllable factors and/or variation from uncontrollable factors. Metrology. Metrology is the science of measurement. The word metrology derives from two Greek words, metron, meaning measure, and logos, meaning logic. Metrology encompasses the following key elements: the establishment of measurement standards that are both internationally accepted and definable, the use of measuring equipment to correlate the extent that product and process data conform to specifications, that is, expressed in recognizable measurement standard terms, the regular calibration of measurement equipment, traceable to established international standards. Units of measurement. There are three major international systems of measurement: English, metric, and the Système International d'Unité, or SI. The U.S. has effectively retained the English system as a remnant of British colonial influence. Units of measurement. The metric and SI systems are decimal-based. The units and their multiples are related to each other by factors of 10. The English system, although logical to us, has numerous relic-defined measurement units that make conversions difficult. Most of the world is now committed to the adoption of the SI system. The SI system was established in 1968, and the U.S. officially adopted it in 1975. The transition is occurring very slowly. The final authority for standards rests with the internationally based system of units. This system classifies measurements into 7 distinct categories. Length, or meter. The meter is the length of the path traveled by light in vacuum during a time interval of 1/299,792/458 of a second. The speed of light is fixed at 186,282.3976 statute miles per second, with exactly 2.540 centimeters in 1 inch. Time, or second. The second is defined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. Mass, i.e. kilogram. The standard unit of mass, the kilogram, is equal to the mass of the international prototype, which is a cylinder of platinum-iridium alloy, kept by the International Bureau of Weights and Measures at Sèvres, near Paris, France. A duplicate in the custody of the National Institute of Standards and Technology serves as the standard for the United States. This is the only base unit still defined by an artifact. Electric current, or ampere. The ampere is a constant current that, if maintained in 2 straight parallel conductors of infinite length, of negligible circular cross-section, and placed 1 meter apart in vacuum, would produce between these conductors a force equal to 2 times 10 newtons per meter of length. Temperature, that is Kelvin. The Kelvin unit of thermodynamic temperature is a fraction 1/273.16 of the thermodynamic temperature of the triple point of water. It follows from this definition that the temperature of the triple point of water is 273.16 K, 0.01 Celsius. The freezing point of water at standard atmospheric pressure is approximately 0.01 K below the triple point of water. Light, or candela. The candela is defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of frequency 540 times 10 Hz and has a radiant intensity in that direction of 1/683rd of a watt per steradian. Amount of substance, or mole. The mole is the amount of substance of a system which contains as many elementary entities as there are atoms in 0.012 kilograms of carbon-12. The elementary entities must be specified and may be atoms, molecules, ions, electrons, other particles, or specified groups of such particles. Calibration. Throughout history, man has devised standards to support those common measurement tools used in trade between various parties. This standardization allows the world to establish measurement systems for use by all industries. The science of calibration is the maintenance of the accuracy of measurement standards as they deteriorate over use and time. Calibration is the comparison of a measurement standard or instrument of known accuracy with another standard or instrument to detect, correlate, report, or eliminate by adjustment any variation in the accuracy of the item being compared. The elimination of measurement error is the primary goal of calibration systems. Total product variability. The total product variability in a product includes the variability of the measurement process. Variance, that is total, is equal to variance in the process plus variance due to measurement. Measurement error. Variance in measurement is equal to true variance plus variance due to error. Measurement error. There are many reasons that a measuring instrument may yield erroneous variation, including the following categories. Operator variation. This error occurs when the operator of the measuring instrument obtains measurements utilizing the same equipment on the same standards and a pattern of variation occurs. Operator-to-operator variation. This error occurs when two operators of a measuring instrument obtain measurements Y utilizing the same equipment on the same standards and a pattern of variation occurs between the operators about the bias between them. Equipment variation. This error occurs when sources of variation within equipment surface through measurement studies. The reasons for this variation are numerous. As an example, the equipment may experience an occurrence called drift. Drift is the slow change of a measurement characteristic over time. Material variation. This error occurs when the testing of a sample destroys or changes the sample, prohibiting retesting. This same scenario would also extend to the standard being used. Procedural variation. This error occurs when there are two or more methods to obtain a measurement resulting in multiple results. Software variation. With software-generated measurement programs, variation in the software formulas may result in errors, even after identical inputs. Laboratory-to-laboratory variation. This error is common when procedures for measurement vary from laboratory to laboratory. The advent of standardized testing such as the ASTM procedures have been developed to correct this type of error. Calibration interval. It is generally accepted that the interval of calibration of measuring equipment be based on stability, purpose, and degree of usage. We have often heard these words but have failed to develop a system that truly adheres to these most basic of calibration principles. The stability of a measurement instrument refers to the ability of a measuring instrument to consistently maintain its metrological characteristics over time. This could be determined by developing records of calibration that would record the as-found condition as well as the frequency, inspection authority, and the instrument identification code. The purpose or function of the measurement instrument is important. Whether it were to be used to measure doorstops or nuclear reactor cores would weigh heavily on calibration frequency decision. In general, the critical applications will increase frequency, and minor applications would decrease frequency. The degree of usage refers to the environment as a whole. Thought must be given as to how often an instrument is utilized and to what environmental conditions an instrument is exposed. Contamination, heat, abuse, etc. are all valid considerations. Intervals should be shortened if previous calibration records and equipment usage indicate this need. The interval can be lengthened if the results of prior calibrations show that accuracy will not be sacrificed. Intervals of calibrations are not always stated in standard lengths of time, such as annually, biannually, quarterly, etc. A method gaining recent popularity is the verification methodology. This technique requires that very short verification frequencies be established for instruments placed into the system, i.e. shifts, days, weeks, etc. The philosophy behind this system is that a complete calibration will be performed when the measuring instrument cannot be verified to the known standard. This system, when utilized properly, reduces the cost associated with unnecessary scheduled cyclic calibrations. Two key points must be made about this system. The measuring instrument must be compared to more than one standard to take into consideration the full range of use. This system is intended for those measuring instruments that are widespread throughout a facility and can be replaced immediately upon the discovery of an out-of-calibration condition. Calibration standards. Any system of measurement must be based on fundamental units that are virtually unchangeable. Today, a master international kilogram is maintained in France. In the SI system, most of the fundamental units are defined in terms of natural standard. In all industrialized countries, there exists an equivalent to the United States National Institute of Standards and Technology, whose functions include the construction and maintenance of primary reference standards. These standards consist of copies of the International Kilogram, plus measuring systems which are responsive to the definitions of the fundamental units and to the derived units of the SI table. In addition, professional societies, for example the American Society for Testing and Materials, have evolved standardized test methods for measuring many hundreds of quality characteristics not listed in the SI tables. These standard test methods describe the test conditions, equipment, procedure, etc. to be followed. The various standard bureaus and laboratories then develop primary reference standards which embody the units of measure corresponding to these standard test methods. In practice, it is not feasible for the National Institute of Standards and Technology to calibrate and certify the accuracy of the enormous volume of test equipment in use. Instead, resort is made to a hierarchy of secondary standards and laboratories together with a system of documented certifications of accuracy. When a measurement of characteristics is made, the dimension being measured is compared to a standard. The standard may be a yardstick, a pair of calipers, or even a set of gauge blocks, but they all represent some criteria against which an object is compared ultimately to national and international standards. Linear standards are easy to define and describe if they are divided into functional levels. There are 5 levels in which linear standards are usually described. Working level. This level includes gauges used at the work center. Calibrating standards. These are standards to which working level standards are calibrated. Functional standards. This level of standards is used only in the metrology laboratory of the company for measuring precision work and calibrating other standards. Reference standard. These standards are certified directly to the NIST and are used in lieu of national standards. National and international standards. This is the final authority of measurement to which all standards are traceable. Since the continuous use of national standards is neither feasible nor possible, other standards are developed for various levels of functional utilization. National standards are taken as the central authority for measurement accuracy, and all levels of working standards are traceable to this grand standard. The downward direction of this traceability is shown as follows. National Institute of Standards and Technology, Standards Laboratory, Metrology Laboratory, Quality Control System or Inspection Department, Work Center. The calibration of measuring instruments is necessary to maintain accuracy, but does not necessarily increase precision. Precision most generally stays constant over the working range of the instrument. ISO 10012 Synopsis. An integral part of the quality system is the documentation of the control of inspection, measurement, and test equipment. It must be specific in terms of which items of equipment are subject to the provisions of ISO 10012, in terms of the allocation of responsibilities, and in terms of the actions to be taken. Objective evidence must be available to validate that the required accuracy is achieved. The following are basic summaries of what must be accomplished to meet the requirements for a measurement quality system by ISO and many other standards. All measuring equipment must be identified, controlled, and calibrated, and records of the calibration and traceability to national standards must be kept. The system for evaluating measuring equipment to meet the required sensitivity, accuracy, and reliability must be defined in written procedures. The calibration system must be evaluated on a periodic basis by internal audits and by management reviews. The actions involved with the entire calibration system must be planned. This planning must consider management system analysis. The uncertainty of measurement must be determined, which generally involves gauge repeatability and reproducibility and other statistical methods. The methods and actions used to confirm the measuring equipment and devices must be documented. Records must be kept on the methods used to calibrate measuring and test equipment, and the retention time for these records must be specified. Suitable procedures must be in place to ensure that non-conforming measuring equipment is not used. A labeling system must be in place that shows the unique identification of each piece of measuring equipment or the device and its status. The frequency of recalibration for each measuring device must be established, documented, and be based upon the type of equipment and severity of wear. Where adjustments may be made that may logically go undetected, sealing of the adjusting devices or case is required. Procedures must define controls that will be followed when any outside source is used regarding the calibration or supply of measuring equipment. Calibrations must be traceable to national standards. If no national standard is available, the method of establishing and maintaining the standard must be documented. Measuring equipment will be handled, transported, and stored according to established procedures in order to prevent misuse, damage, and changes in functional characteristics. Where uncertainties accumulate, the method of calculation of the uncertainty must be specified in procedures for each case. Gauges, measuring equipment, and test equipment will be used, calibrated, and stored in conditions that ensure the stability of the equipment. Ambient environmental conditions must be maintained. Documented procedures are required for the qualifications and training of personnel that make measurement or test determinations. Summary: Measurement system analysis. In this lesson, you learned about the following. What is precision and accuracy? What is bias, linearity, and stability? What is gauge repeatability and reproducibility? What is variable and attribute MSA?